I hope you can hear me. It's 2 o'clock Eastern time, so we can get started. So today we'll mainly focus on two-dimensional sampling, and really the objectives of what we are trying to do today are the following. First, we'll study the rectangular sampling of two-dimensional signals. And rectangular because you can imagine it's in a direction of x and y. So it's a natural extension of the one-dimensional sampling. And then we will take that and generalize it for different sampling lattices. And then that will lead us to understand the concept of sampling density and introduce from there what would be the density if we have a special spectral density and sampling lattice for a given signal. And then the overall plan is really to understand how we can apply these concepts when we have a downsampling or upsampling framework. And once we have upsampling, then that will lead us to the interpolation framework that we briefly mentioned in the last lecture. The main purpose, as we are all deal with digital signals and digital images nowadays, but really understanding sampling, the generalized lattices for two-dimensional sampling, it provides quite a bit of an intuition about images and imaging in general. So that's really the main purpose of this lecture. So the outline, we'll spend some time on the periodic sampling and rectangular sampling specifically. And then we generalize that and we look at some lattices and examples of lattices. And then we briefly look at downsampling and upsampling. So first of all, let's just kind of revisit in the 1D case, this analog versus digital ideas. And the first signal on the upper left corner is an analog signal. You can see in the x-axis, we have the time axis as continuous. And the y-axis, we have our function y of t. It's also continuous, meaning that can hold any values, not necessarily integers. And then we can go to next to it, and we have in the x-axis we have time, but this time in here is continuous time, while the values for the signal y of t, they only take certain discrete values. They can be integer or some other values. So in this case, you can see in here the values are 0, 2, 4, -2, -2, and so on. So these are the discrete values our signal y of t can take in this case. So this we call it continuous time discrete value signal. And then in here what we have a the time axis. It can only take discrete values, and you can see those are pointed out in here. And however, the y-axis can, or the signal y of t on the y-axis, they can have continuous values. So in this case, we call this a discrete time continuous value signal. And then finally, we go to the digital signal, which is on the time axis. The time is really split into discrete events. So this is discrete time. And the y-axis or the y of t can only take discrete values as well. And then in this case, we have a digital signal. So both the time axis and the signal itself are both discrete in time and in value. So you can see we label the discrete time continuous value as our sampling, right? And once you have this sampling and then you digitize your signal, for example, you sample your two-dimensional plane, and then you say, I want to represent the values of the image or the values of y of t using a 2-bit sequence or a 3-bit sequence. In that case, you are doing a digitization. So you are sampling in the time axis, or you are sampling in the spatial plane. And then once you start to have a digitization of the values that each sample could be represented with, then that basically you are digitizing the values of y of t, or the two-dimensional signal y in the 2D case. We can revisit the sampling theory, but now we bring the two-dimensionality, which doesn't really affect much what you studied in undergraduate. And if you remember, a band-limited continuous image or signal may be reconstructed from its sample values when the sampling intervals in both directions, horizontal and vertical, are small enough. Or in other words, the sampling frequencies are large enough. And if you remember, we had the Nyquist sampling, the Nyquist-Shannon sampling theorem, which states that if a signal or an image have the highest frequency as B, then the sampling rate should be at least 2V to reconstruct the original signal from the sample. So we will look into rectangular sampling first. That is basically the lattice is going into the X and the Y. And then we will extend that to other types of lattices. So some definitions in here. So this is an A to D converter. The input from the left, I will label this as small f sub a for analog. So this is a spatially continuous image, f sub a of x and y. And then on the other side, the output, I have my discrete signal f of m and n. And then if you notice in here, I'm calling f of m and n is equal to fa, I'm sampling the x with this capital X, actually the M, sorry, capital X, and the N with capital Y. So capital X and capital Y, respectively, are the horizontal and the vertical sampling intervals or period, meaning that if this is my x-axis, this is my y-axis, and then imagine that we have a two-dimensional continuous signal covering this plane, then what you used to have in the 1D case, we have capital T, so that's the periodicity of our sampling. And here in the x-axis, we have capital X, we have 2x, 3x, and so on. And in the y-axis, we have capital Y, we have 2 capital Y, 3 capital Y, and so on. So that's why the name rectangular sampling or rectangular lattice is coming from. So we have an input FA, that's analog, and then we have an F of M and N at the output, which samples the input FA based on a rectangular lattice in this definition. And that rectangular lattice is defined using two numbers, the capital X, which is the periodicity or the intervals of sampling in the X direction, and capital Y, which is the periodicity or the sampling interval in the Y direction. Also in this definition that we are trying to really follow throughout the lecture today, I'm defining the Fourier transform for the continuous signal as capital F sub A of phi and omega, and then the Fourier transform of our sampled image as capital F of mu and nu. So these are two Fourier transform of these two signals. So if we have that, just a remark in here, a reminder that don't confuse sampling with the periodicity vector that we had to describe patterns or signals that have a repeated pattern. And you have one of those in the homework questions. So here is an image on the left-hand side from the images archive. And then the one on the right, this is sampled. I forget the rate of this one, but it's really a very, very um, low rate of sampling. And you can see basically the majority of the image detail still is preserved. Just to show you basically that depends on the images content, you still, even if you downsample quite a bit, you still maintain quite a bit of the architecture and the structure and the details in the image. Okay, so let's really dig into our signals. And the first thing I would like to introduce is the definition of in the analog space as we input the signal to A to D converter. Before we go there, we have our continuous signal F sub A, or analog signal F A of X and Y. And then we calculate the Fourier transform of that analog signal and using the Fourier transform definition for continuous signals. So the difference in here that we already have double integration because we are looking at X and Y, or phi and omega in the frequency domain. And now, so this is definition of the Fourier transform of analog signals. And now the second thing is how we are obtaining our digital signal F of M and N from our analog signal FA. And for this specific situation, we have a rectangular lattice. And then we can replace the small x with M as an index, and capital X, which is the sampling interval in the X direction. And we replace the small y with N, which is the index for our discrete signal F of M and N, and capital Y, which is the sampling interval in the Y direction. So for example, imagine that we have capital X is 2, capital Y is 3. Then if we look at the value of our signal FA at 12 and 12, basically you can think of this as small x is equal to small y is 12. There's one point in the continuous two-dimensional plane. Then by definition, this signal, or this point FA at 12 and 12, will be mapped to F of 6 and 4 in the discrete signal, in the digital signal, because capital X is 2 and capital Y is 3 in this. So now you can see from here, back to some of the questions that were mentioned, yes, there will be cases where not all pixels in the discrete signal, digital signal F of M and N can be filled out from FA, because that mapping may not result in an integer index. And in that case, we need to really invoke our interpolation algorithm to fill out these undefined values in this lattice. And we'll worry about that later today. But for now, all what we need to focus on is just kind of the convention, the introduction of these terminologies, and the definitions of these sequences, and their Fourier transform. So there are two questions we'd like to answer in the first 20 minutes of this lecture. The first question is, what is the relationship between the Fourier transform of our continuous signal and the Fourier transform of our digital signal? And the second question is, when can we reconstruct our analog signal from discrete signal, which is something covered by the sampling theorem? So let's look at the relationship between the Fourier transform of the analog signal and the Fourier transform of the digital signal. So the first two equations, as you can see in here, these are from the definition of the Fourier transform of a continuous or an analog signal. And then in here, this equation determines the relationship in the spatial domain of how we can obtain the sample values in our digital signal F from the analog signal FA using the sampling intervals or the sampling period capital X and capital Y. So capital X, capital Y, these are numbers are defined for our sampling lattice in this case. So similarly, if I use this equation here, right? And then on the x-axis the same. The y-axis, I replace FA with the definition from this equation, as you can see in here. So now what will be different is that I will replace small x with M capital X. I will replace small y with N capital Y, because that's how I can get f of M and N. So now I have this equation on the left-hand side. I have our digital signal f of M and N. And on the right-hand side, I have an expression that involves the Fourier transform of our analog signal. And then there are these sampling lattice numbers, which are the capital S and capital Y that are predefined or are scalar values in this case. So we take that equation. This is the same equation here. And now we will introduce some kind of change of variables. So the mu is equal to phi times capital X, and the nu is equal to omega times capital Y. And then I plug these new variables into the equations. I get this equation here. Okay. So now I have an equation in the middle there that has, on the left-hand side, I have my discrete, my digital signal f of M and N. And on the right-hand side, I have a double integral. And the main function, the main sequence I have there is the Fourier transform of our analog signal. So now, if I remember from last time, we said the Fourier transform and the inverse Fourier transform. I could write f of M and N as double integral using the Fourier transform of small n. So this is, remember, this is the analog Fourier transform. This is the digital Fourier transform, right? Meaning that is the Fourier transform of the analog signal and the Fourier transform of the digital signal. So now from these two equations in here, the left-hand side are the same, equal. So, but the right-hand side, that means it must be equal. They must be equal. Although one of them is defined over using the Fourier transform of the analog signal, while the second one using the Fourier transform of the digital signal. So we'll write them down here. And now, if you look carefully, comparing these two equations, as I mentioned, the left-hand side are equal. That means the right-hand side also must be equal. What you observe, there's a few things that we need to look at. The first thing is the terms basically on the integrals. So this covers negative infinity to infinity, and this one is one tile of 1 by 1 dimension, or between negative 0.5 and 0.5. And then what I have in here is f sub a, and then here I have capital F. So now I can say the first equation, that integral is really, I'm doing the integration over the entire plane in the mu and nu space. And then in the second equation, I'm doing the same thing, but now I'm doing the integration over only a single tile in the plane. And then tile is 1 by 1 dimension. And again, both of them will give me the same answer. So I could conclude from there the following, that from the first equation, I'm doing integration over the entire two-dimensional plane, the entire plane of mu and nu, and I'm getting some quantity. In the second equation, which is at the bottom here, I'm doing the integration over one tile. So in a way, this one tile in this space in the second equation is having all the energy and the quantities that are there on the entire two-dimensional plane once it's defined over FA. So what I could say that if I take FA in here, right, and I try to take from the entire new two-dimensional plane where F sub A is defined, and basically I take every one by one tile and I keep bringing it into the unit tile at the location 0. Once I have covered the entire infinity both direction plane, then what I have there is equivalent to the Fourier transform of our digital signal. In other words, for these two equations to be equivalent, to be equal, and they are equal because the left-hand side are equal, then there has to be a relationship between FA and F, where F, the Fourier transform digital signal defined in here with the integration over one by one tile, it has to basically encompass the entire energy that our F sub A has in the entire two-dimensional plane. And of course, we have capital X, capital Y in here as scalars, so we have them. So what this equation is, what this is doing, I'm going to F sub A, and I keep shifting it with these integers K and L, and I keep basically bringing it to really kind of create that one by one tile that will give me this. So now once I do that, then this explains why I have these two equations in here that are equivalent to each other. Although one is defined over the entire plane, the other one is defined over a single plane, because that capital F over that single tile is equal to the entire plane when it's once defined over F sub A. So now this gives you an idea about the relationship between the Fourier transform of the analog signal, capital F sub A, and the Fourier transform of our digital signal, capital F. So remember the change of variable that we introduced, that mu is equal to phi times x and nu is equal to omega times capital Y. I could really bring that expression back. And now what I have on the left-hand side, the Fourier transform as a function of phi and omega, as if I am sampling in the frequency domain, is equal to 1 over xy, summation over k and l, double summation over k and l, and then I have the f sub a. So now I have an equation in terms of capital X, capital Y, in terms of phi and omega, that give me the relationship between f sub a and f. So now the question is, so this is a general relationship between FA and F. We have not made any special assumptions about FA or F in this case. So now let's move and bring, so that what if A have overlaps? Can we wait for that question when we have an example? Because this overlapping that's why the capital X, capital Y, and the maximum non-zero frequency component in FA, all of these will be together. Okay, and the question of this overlap, it has to do with the second question we're trying to answer, which is, can we reconstruct if A from F? So I will hold on to that question until we get to that stage with an example that illustrate that concept. So back to what I was saying about, we haven't made any assumption yet about if A or F. So now the next thing we'd like to see this relationship between FA and F in the case when our signal is band limited. Okay. So now we can make an assumption that F sub A is really band limited signal. That means it is zero outside a certain region. And here is the relationship equal to a zero when phi is larger than or equal to 1 over 2x and omega is larger than or equal to 1 over 2y. So basically it's a band limited within between negative 1 over 2x and 1 over 2x in the x direction or the phi direction, and between negative 1 over 2y and positive 1 over 2y in the y direction. So in that case, this relationship, the generalized relationship between f and f sub a, become this relationship in here, meaning that as far as yeah, this here says when as far as phi is between negative 1 over 2x and 1 over 2x, and between negative 1 over 2y and 1 over 2y, then I have an identical equality between f and f sub a with just a scaling factor of 1 over xy in this the right term. So now what this means that if I have a band limited signal, right, and that band limited signal satisfy, or the maximum bandwidth satisfy this condition, which is expressed in here in terms of our sampling periods, capital S and capital Y, right? Our sampling intervals that we introduced early on. If that condition is satisfied, then now I have an equality between capital F and capital F sub with a scaling factor, of course. So, so the best thing is to look at this example in here. This is just a very generalized example, just for illustration. And then what we have on the left-hand side first, what I have here is capital F sub A. So capital F sub A, imagine I'm looking at this as a disk. And then within this disk, there is a value of, let's say, 1 or some kind of a scalar, and then it's 0 outside. And this is phi, and this is omega. So now when I'm doing, I have a specific condition here, which is basically the maximum on the phi axis or in the omega axis is W, right? So it's this W in here. And this W is much less than both 1 over x and also 1 over capital Y. What are the capital Y? These are our sampling. If that's the case, again, everything in the slide we are looking at in the frequency domain. Then what's really happening, if you look at the generalized equation here, what I'm doing, I'm taking the way I'm calculating this part of the slide is an illustration of how the Fourier transform of our digital signal looks like. So this double summation here means that I'm doing what? I'm shifting and bringing, that means I am doing a repetition of our disk. So now the first thing is really when k is equal to a 0 and L equal to a 0, then I'm having the original disk as is. Right? Now, if these conditions are satisfied, now the next repetition, if I go to the k is equal to a 1 and L is equal to a 0, then I'm at this copy, right? And the shift will be 1 over x, which I have in here. And the next one, when k equal to a 0 and L equal to a 1, I'm shifting up. So I'm having this copy in here, which is 1 over y. If k is equal to 1 and L equal to a 1, then I'm at this copy in here, and I'll keep doing that. So that's basically how the spectrum of our digital signal looks like. As a refresher, the most common example that you most likely you covered in your undergrad class was when you have the spectrum looks something like this triangle, and then when you are sampling, you bring it here, and then here, and then here, and so on. All right, and this is the frequency domain. And then this here is 1 over t, this is 2 over t, this is negative 1 over t, and so on. So you have that in the 1D case. It's the same concept in here. That's why we are introducing a rectangular, because it's just now you do the same thing, but in the 2-dimensional case. And now we don't really have one capital T, we have two of them. We refer to these as 1 over x and 1 over y. So the same, you continue. This is 2 over x, this is negative 1 over x, and so on. You go to, so you really have the limits in here are between, for k and l, between negative infinity and infinity. You really repeat that throughout the whole two-dimensional plane in the frequency space. So the in short, what you really need to, the getaway message from all of this is the following. In the 1D case, we have capital T controlling our sampling interval or our periodicity in the frequency domain. And when you are sampling a spectrum, it can be a triangle just for illustration purpose. Then if the signal is band limited with the maximum frequency in the signal is less than 1 over t, then the fact that I'm sampling means that I am doing this repetition of my spectrum. The same concept in a two-dimensional case. The only difference now I have capital X and capital Y to really determine our sampling in the X direction and the Y direction. As far as the maximum frequency in our spectrum of the analog signal f sub a is less than 1 over x in the x direction and less than 1 over y in the y direction, when I'm repeating, I don't really have an overlap between these. And then in a minute, we'll know why that is important. But this is kind of just an illustration of what the meaning of this equation that relates capital F sub A and capital F. So now, imagine that once you have your digital signal, and then you plot basically the spectrum for negative 4 pi to 2 pi in both direction, for example. Then just for the purpose of illustration, you will have something like this. Right? And now, as in the right-hand side. And now, if you remember what we had before, we had in the 1D case, we had our triangle. And then we say, if we really want to reconstruct our signal, either to play an audio, for example, on the speaker of the computer, then we go and sample between negative pi and pi, right? The same thing in here, what you would like to go and sample between negative pi and pi, and negative pi and pi in here. And then now what we have an exact copy of our spectrum. Yes, there is a scaling factor of 1 over xy, but that's easy to deal with. And then I can really recover an exact recovery of our signal. I can play this capital F sub A or display it. Now, the problem happens when, back to the question from one of the students, what if I have an overlap? What if this part in here and this part in here, the relationship between the maximum frequency, which is W in the X direction, and the value I chose for my sampling, the sampling lattice in the X direction, capital X, if they don't satisfy this condition where W is less than 1 over X. So in that case, if there is an overlap between these two disks together, and imagine I have, let's see if I have that example. Yes, imagine if I have the case where I have something like that. This is my disk. This is the next one. This is the next one. Next one. And so on. So my capital X, capital Y, they don't satisfy that condition. So in that case, so if you look in here, this in here, if I really want to come and say, I want to go between negative pi and negative pi and pi in the y direction, what I have, I don't really have the exact copy that I had before. Right? I have some overlap between these repetitions of this disk, right? So that will introduce some distortion to my signal here, right? This is distortion, distortion, distortion. I cannot recover our f sub a back, right? I cannot recover it back. And that basically means I have aliasing happening. Uh, so aliasing in this case is happening in both directions, or it can happen in one direction. So maybe capital X is satisfying the condition, but capital Y is not, or vice versa, or both don't satisfy, as in this case. So in that case, I have aliasing happening, and then I cannot recover or fully recover the signal capital F sub A back, or F sub A back. So now what we showed so far, that for a band limited signal, we can recover the capital F sub A from the Fourier transform of the digital signal using this equation here. And then keep in mind, which implicitly we are using capital S and capital Y that satisfy these conditions. So now the next thing, if that's the case, then I can really recover FA from F. Let's see how we can derive that. So by definition, from the Fourier transform, this is the inverse Fourier transform in the analog case, that FA of X and Y is equal to the summation of FA e to the positive J2 pi phi X plus omega Y. And now what we will do is to say, I have this relationship of FA, which is from here. I replace FA with this definition. So FA becomes XY times F of phi X omega Y. And now the limit of the integrals become between negative 1 over 2y and 1 over 2y, and negative 1 over 2x and 1 over 2x. So this is the relationship between FA and our capital F in this case. However, we have a definition for our Fourier transform digital signal, which is obtained here from previous lecture as double summation of f e to the negative j2 pi mu and plus mu. If we can bring that in, which is in here in this case, I can rearrange some terms. What I will end up with is the following: double summation over m and n, and then I have f of m and n, and then I have the sinc functions. Right? The sinc function. If you remember, in the one-dimensional case, we could ideally reconstruct our signal using a sinc function. Right? We go to every single sample, and we have a sinc function, and we keep shifting. Right? Now, that's why I said rectangular sampling is a very natural extension of the 1D case, because now in this reconstruction, we have two sinc functions, one in the x direction, the other one in the y direction. You can imagine that every single sample, we have our sinc functions, one in the x direction, the other one in the y direction. And that's how we reconstruct our signal, because we are interpolating between these sinc functions. So that's the ideal reconstruction of our analog signal, our analog two-dimensional signal f sub a, from the discrete signal f in this case. So now, what we have been doing so far, just fixing. Okay, so so far what we have been doing is that for a two-dimensional signal, as far as we have a band-limited signal, and our choice of capital X and capital Y satisfy the conditions on this band-limited signal, then we can fully recover our signal, at least in theory, using the sinc functions. And then when we talk about, remember, if in the interpolation discussion we will have next week, we cannot really implement the sinc function in the computer completely. So we have approximations. We have the zero order hold, and then we have bilinear, and then we have bicubic function that approximates the sinc function. We'll see about this next time we talk about interpolation. But for now, at least we have determined the conditions of when we can fully recover the signal if we are careful about the choices of capital X and capital Y. So we have some examples in here. So the first image that labels number 1 in this case, this is an image. Everything there is 0, except for this line that has a sharp zigzag kind of pattern in it. And then overall, this line from the top to the bottom is just a single line with a slope of 5. And then when you, from last lecture, when we talk about the Fourier transform properties, we know that if we apply a Fourier transform, then what we are expecting is a line with a slope of -1/5, right? Which what we have on the right-hand side in here. So we have this line. However, if you look carefully, we have more copies of them, right? And these are the copies of the spectrum that are obtained from the aliasing effect, which is the same as what we have in here. So these are the copies that we are really getting in here. We have this aliasing in here that's happening because of there was this question about what do we mean by high frequency. These transitions, this sharp transition between 0 and 1, they really contribute to the high frequency. So these are high frequency content. Some of them have direction in the x direction, some in the y direction, some in both. So it depends on basically what is this? Is this line a vertical line, maybe horizontal line, maybe there's a slope to it. So they contribute in a different way to the phase in the frequency domain. In general, what you can look in here is we have the -1/5 slope that we are expecting, and now we have these multiple copies, right? So if we apply an anti-aliasing filter, or what we call a directional filter, meaning that a directional filter basically is a filter where it is designed to keep a certain direction in the frequency domain and filter out everything else. In this case, it's really keeping only this copy that has the -1/5, and then filtering out all the other copies. This copy in here, this copy in here, this copy, and this copy. All of these are filtered out. And if I get this one here and then apply my inverse Fourier transform to go back to the spatial domain. So this is spatial domain, this is spatial domain, 2 and 3 are the frequency domain. And then once we get to the DFT, we'll study how we can plot these using DFT. So what you observe, we got this image, we apply Fourier transform, we visualize that Fourier transform here, we applied an anti-aliasing filter. So this is how it looks like as number 3 in the frequency domain. We apply inverse Fourier transform, and here's what we get. And you notice the difference between 1 and 4 is that 4 is what? Is smoother. It's more blurry, meaning that the transition between the 0, the black pixels, and the white pixels in here are more blurry, more smoother than what you have in here. Why? Because we apply what we call as anti-aliasing filter in here. And it's a very, very common practice in image processing. As soon as you really start processing the image, look at many of the codes out there. The first step is just one line to apply an anti-aliasing filter to get rid of all the sharp edges in the image, just to make sure we don't really deal with aliasing. However, the main reason is really the high frequency content usually is where the noise is happening. So you are just filtering out the noise, although you are sacrificing the quality and the smoothness and the sharpness in the image. But it's a common practice because of this. For analytical reasons, for applications like segmentation, detection, and so on, number 4 in here, you still have that line with a slope of 5. You don't have that zigzag and sharpness in there. It's much smoother. So it's still a very important piece of information for the segmentation. We'll talk about that in a minute. So if I take the cameraman and I apply the code to visualize the DFT, and you can see in here, we have all these lines passing through the origin, which is the DC value. But you obtain what we have in yellow. We have this line here, we have this line, which are really coming from the replicas of the spectrum as we did in the disk illustration example. our sampling. You can think of it this way: our sampling of the cameraman is in the X and the Y direction is not really satisfying the highest frequency content in the cameraman image because of the with that frequency content. As I mentioned in one of the questions on Piazza, if you look at this edge in here, all these edges, all these edges in here around the tripod legs, all this transition between really um, uh, intensity values, they contribute to the high frequency content. Same thing in here. There's very localized in the grass in here, this region, but we cannot identify them by pencil. But there's quite a bit of transition between intensity values that it contributes to the high frequency content. So there are some examples, and I put GUIs, a MATLAB one that was for 2018 MATLAB, and the other one that was developed by one of the former students in this class. And you can look at the README file in both cases to know how to operate the GUIs. But you can really input this kind of signals and this kind of images to see what's really happening. So if you look at this brick wall image, and then you have a sampling size of 1/8, meaning that from every 8x8 tile or 8x8 block, from every 64 pixels, you keep one. That's our downsampling. And with the anti-aliasing filter, this is the image we'll obtain. Without the anti-aliasing, this is the image we will get. So you can see in terms of at least perceived quality with the anti-aliasing is less distorted than the one without the anti-aliasing filter. So far, what we have done, we look at the relationship between the Fourier transform of the analog signal and the Fourier transform of the X of the digital signal, and we look at the relationship between them, and then these are the equations governing that. And the reconstruction using the sync function. Let's me get to the questions. Oh, yeah, you get that. So basically, you get some kind of, if you go to the GUI, if you go and zoom in, see this, this is basically what you will get, this kind of artifacts that you will be getting. In here, you are really maintaining the fundamental structure of the pattern in the brick wall is maintained, right? You don't have those distortion from the aliasing effect that you have in this case. So that's really the main difference between applying an anti-aliasing filter and not applying an anti-aliasing filter in this case. Second question about the phase component of the anti-aliasing filter. We really rarely, when we talk about compression, we'll touch base on the phase. All the discussions that we are having so far, all what we are showing is the magnitude of these filters and the Fourier transform. When we get to the compression, we'll look at how you may use the phase, denoising as well. There's quite a bit of study of the phase in that case. Okay, so now what we'll move next. So now we have the rectangular sampling. It's simple in the sense that it's a rectangular extension of the 1D case. So instead of capital T, we have capital X, capital Y. Everything else is the same in terms of conditions on the band limited signal, as well as how we can reconstruct using the sync functions. So now we would like to kind of generalize this, and the main motivation is really give us quite a bit of an insight into the sampling process. Maybe will help us to design better imagers that sample the light field, And we will see basically that how the rectangular sampling, although for the hardware implementation, makes things easier in our images. However, it's not really the most efficient way to sample a multidimensional signal. And we'll study how the human eye is really sampling the light field. So before we get to the generalized periodic sampling, I'd like to introduce this notation, which we had introduced before, that we will replace our vector of m and n with this two by one vector. We call it n, and in that case, what we could do is we say if a of boldface x, small x, this is the same as if a of x and y. F of boldface n is the same as f of m and n. Fa of boldface omega is the same as Fa of, capital F of phi and omega. And f of boldface mu is the same as f of mu and mu. It is nothing but really just to make things look a little bit neater, nothing more than that. And then if we really integrate that into our equations, then we can replace our double integral with one integral, because x in here is defined over x and y, same thing in here, zeta here, phi and omega, and so on. So, this is really kind of hopefully will make the generalized sampling a little bit clearer. Yes. So this one is the next example. So what we have f of m and n. I would like to call this is equal to f a. Before, when we had the rectangular, it was very simple. I have capital X, right? And M capital X, right? We had before, if you remember, we had M, X, and N, Y. Right? What I want to do now to generalize this, so that f of M and N is f A. And now instead of having just two scalar, capital X, capital Y, I would like to introduce a 2 by 2 matrix. A 2 by 2 matrix. And then what I will have in here is M and N. If I had before as X and 0 and Y, then that's just the special case, which is X, M, X, and NY. Right? So now that's what we have on the right-hand side. Right? So now, if I don't really have these as zeros, then I have a generalized sampling. I don't have the rectangular sampling anymore. So now this equation here, we'll call it as bold x. These numbers in here, these four numbers in here, will define our sampling lattice. If I have them as capital X and 0 and capital Y, then I have the special case as a rectangular sampling. If I have them as capital T and 0, 0 and 0, then I have the special case of what? One-dimensional sampling. But I'd like to can generalize this to the general case. So to visualize this, you can look at this. This is our sampling lattice. This is, imagine we have a two-dimensional continuous signal, and then I'm defining boldface x1. It has two numbers, and the second vector in here, boldface x2, it also has two numbers. Together with these, they will define our sampling matrix. A 2 by 2 matrix. Okay. So this is the first vector, and this is the second one. right? So now these two together, they will define our sampling lattice. In the case when we had capital X and 0 as our x1, and we had 0 and y as our second vector, what we had was we have x and we have y as our sampling lattice. So it's a I'm hoping this kind of illustration can make things a little bit easier in this aspect. So if we this is just an illustration of what I was talking about, and then here are some of the popular ones. So remember when we had the rectangular ones, we've had x11 as capital X and x22 as capital Y, what we have been discussing since the beginning today. And then we have the hexagonal lattice, and then we have the quincunx lattice, and then we have the one-dimensional case. And alpha is a variable, is a parameter in this case. So all of this is just I'm trying to kind of introduce what this means. So if you go to the GUI, or you can just look at these slides in here, we have different examples of what's happening, right? So the first thing is, if you look at the rectangular one, capital X and capital Y don't really have to be equal. So x11, x122, for the generalization purposes, don't have to be equal. So if I choose this to be equal to 40 and 01, then I will be downsampling this brick wall image to this image on the right-hand side, the upper right-hand side, right? So I'm picking one in every four columns, right? And I'm picking every single row as it is, right? So I have this kind of shrinking in the horizontal direction, and the y direction is the same dimensionality. If I am picking every other column and every other row, or I'm picking one pixel from 2 by 2 neighborhood, then what I'm obtaining is 1/4 of that image. And the same thing in here if I have 3 and 4 as well, or 3, 0, and 0 and 4 with our vectors. Now, this specific image in here, which I think we have it, most likely we have it in the image archive. And the main purpose of this image in here is really just to give you an idea of what's really happening when you have more than just a rectangular lattice. So for this specific case, rectangular lattice, you can see I'm picking every fourth. So I'm picking 1, 2, 3, 4, right? The next one will be this one. The next one will be this one. And that's what I have from that row. And then for the next row, I'm picking this. I'm picking this one, and so on. And that's what I have in here. So you can see basically this example, this image, just give you kind of a toy example of how things evolve. And these things are really easy for that purpose. But now, when we go to hexagonal, on the brick wall image, this is really what's happening. And if you look more carefully at this example will tell you not only because now I don't really have any more x11 and 0 and 0 and 1 and x22. What I have in here is all these numbers are not 0. So there is a rotation happening. So I'm doing a rotation, and in a certain direction or axis, I'm sampling. I'm picking up every certain number of pixels. So if I have alpha equal to half in the hexagonal sample, this is what I have. See all these pixels in between, these black ones in here. All of these, we kept them as they are, and because black, and that means we just assign them the value 0. What will happen once we have interpolation, then we will fill these out with some non-zero values. But for now, for the sake of just this argument, we'll just keep them as they are. If alpha is equal to 1, I'm doing this, which is a little bit different rotation, and you can see that from here. See, this is the triangle. This is the triangle, and we have alpha equal to 1. That's different from when alpha is equal to half. Different rotation and different shrinking in different direction. And here's alpha equal to R2. So you can see as you increase alpha, then you are really doing more and more downsampling. You are really making more and more uh, noise or artifacts. The same thing in the Quincunx case. You can see there's this kind of similar effect, although relatively identical. This slide in here just show you, although visually maybe they look the same, but in reality actually the look at the edges here, they are not the same, these two. So this is you can see basically that from the whole purpose of this is just to give you an intuition of that there is this rotation and there is kind of a shearing effect happening. You're really sparsing certain pixels up far from each other. It depends on alpha is larger than one or less than one, and then in what direction. So um, so that's really kind of the intuition I really want you to have. But don't expect that I give you an image and then I expect you kind of to really draw me what the image. I mean, you have Claude and MATLAB and Python and other image processing toolboxes to do that for you. So I'm just going to make sure I'm covered. Yes. So the next thing I really want to talk about is this concept. Yeah, we have 15 minutes, so I want to introduce this concept of sampling density, which is really important. So this whole slide in here is all about just all the equations that we had before. We are introducing them again using this vector notation. And what the purpose of this one here is to say we can really rewrite everything using this. Let's see the boldface X, boldface omega, and so on. However, what we're going to talk about in more detail is this factor here. So two things. One is this equation here, that if you think about what's really happening in the sampling of a two-dimensional image or downsampling, imagine you have a continuous two-dimensional plane, and then you have this field of unit sample, which are really nothing but impulses. So you have a field of impulses to tell you basically your lattice. Right? And now you are doing a product between your analog signal here and between your field of impulses or unit samples, as we call them, which are governed by the lattice that you are applying. So this product in the time domain, the spatial domain, is nothing but what? A convolution in the frequency domain. So now what we have, we can really define this PA of X, which is really PA of X and Y. This is the field of impulses as our, as nothing but really deltas that are shifted all around the two-dimensional space. But that shifting is controlled by our sampling matrix, capital X. Remember capital X is X11, X12, X21, and X22. So this matrix in here is really controlling basically how this field of impulses look like. If it's capital X and 0 and 0 capital Y, then we know exactly basically this rectangular shaped kind of field of impulses. That in the general case, basically, we can redefine this as a matrix, capital X, the 2 by 2. And then now, this field of impulses from the Fourier transform properties and table that we had last time, we know basically the Fourier transform of this field of impulses is really given by this field of impulses. Right? But it really introduced in the 1D case, if you remember what we had, and this kind of we call it, depends on what textbook, but we call it train of impulses in the 1D case. Remember a train of impulse, like one impulse after the other, and the space between them is capital T. In the frequency domain, the Fourier transform of that is 2 pi over T. And then again is another train of impulses that's basically sparsed by 2 pi over capital T. Is the same extension here. Instead of having capital T in the denominator, we have the determinant of x. In the rectangular case, will be capital X times capital Y. And then on top of here, we have 2 pi to the n. And we'll talk about that. And in this case, it's 3 square. The two-dimensional case is 2 pi square. Capital M is 2. And then what we have in here is this basically capital omega in this case. This one here, in the 1D case, it was 2 pi over t. Right? In this case in here, you can think about that as if I'm having this capital omega matrix times the transpose of our sampling matrix X, which is this one here, then the product between the two will give me the identity matrix. So now you are starting to see where we are heading. So just to introduce kind of what whole thing is about, let's look at this relationship between this vector mu, this vector omega, which is really phi and omega. This one here is in mu and mu. And then the sampling between these two. So the relationship between the frequency variables of the Fourier transform of our discrete signal. Remember capital F of mu and mu, and the frequency variables in the continuous signal, which are phi and omega. The relationship between them is really controlled by our sampling or the transpose of our sampling matrix, capital X. In here. Or you can think of it as is really controlled by this capital omega, which is obtained by using this relationship in here. This relationship in here between the sampling matrix and our capital omega. So now I'm going to jump to something. Where it is. Just give me a minute. Something I think I skipped. No. Yes, here. Here. So this omega, this capital omega in here, I want to define it as our periodicity matrix. And remember, what's this relationship between this capital omega and x is really nothing but this one here. That if I multiply the x transpose by this capital omega matrix, then I get the identity matrix. So I will define this new 2 by 2 matrix as our periodicity matrix for now. Now, all of this, basically, what does this mean to me or to you? That there is a relationship between our mu and mu, right? And our phi and omega. These are in the continuous case, and these are in the digital. Meaning what? These are frequency component of the digital signal. These are frequency component in the continuous signal, and then our sampling, whether we are rectangular or we are doing some other 2 by 2 sampling matrix, or I can describe that using our periodicity matrix, which is the capital omega. In sampling in general, we are mapping between the frequency variables in the continuous domain and the frequency variable in the discrete domain. And that mapping can be as simple as if x is diagonal, that means I have a rectangular, that means our x has some number x0 and 0 and y. It's a diagonal matrix. Then all what we have between the relationship between these frequency variables and these frequency variables will be nothing but what? Scaling factor. Right? We are really scaling this frequency variables. If it's not only diagonal, if I have these are not 0, like x11, x12, x21, and x22, these are not 0, none of them is 0, then what we have is more of an affine transformation. So I'm doing scaling and rotation and shearing, as we have seen in the examples of the hexagonal case. We have rotation, we have shearing in one side, and then the other side, which is within a certain degree from the previous axis, is also we are doing some kind of a scaling. So this is kind of just to give you the relationship between or the impact of our sampling lattice on the relationship between the frequency variables in the of the discrete signal and the frequency variables in the of the continuous signal. Um, okay, so let's look at kind of after introducing this. I know it's just quite a bit, but let's just take a step back and say, let's look at what we had. Remember the example that we had before when we had a disk and the maximum value in the disk is capital W. That was the Fourier transform of the spectrum of our analog signal f sub a. This is the one here in the upper diagram. And now if I have our sampling periodicity matrix, right? So I can define it as capital X, that's our sampling. This is what? This is in the spatial domain, right? As if I was doing capital T, right, in the 1D case. Or I can look at omega, capital omega, in the frequency domain. And this was what? 1 over T or 2 pi over T in the 1D case. Right? It's the same concept in here. If I'm looking in the frequency domain as I'm looking here, this is frequency domain, right? Then now the two vectors that are defining the replicas I have in the frequency domain, either as in the rectangular case we had, remember the example we had 1 over x and 1 over y, right? And then 2 over x and 2 over y and so on, in the same thing in the negative directions. In this case in here, 1 over x and 1 over y, these are really omegas. So in that case, if I have x here, I have 0, I have 0, I have y, then omega in this case is 1 over x, 0, I have 0, and 1 over y. In the general case, I will call the first column in here is omega 1, and the second one here as omega 2. And that's exactly what we have in here. So these two vectors in here are defined or are defining what is our replicas or our periodicity vectors in the frequency domain. Right? And remember, we had that relationship where omega, capital omega times x transpose is equal to the identity matrix. Or you can look at it using this one, or you can even simplify it just using the rectangular case as an illustration. And then I would conclude with this definition. Why we are doing all of this? All the last, I would say, confusing 15 minutes are leading us this definition, the sampling density. The sampling density is, this is defined as, is 1 over the determinant x. What is 1 over determinant x? Is the spatial domain area that associated with every single sample. So if I have one sample, then I can look at the area, the energy that this sample is representing from the continuous case is really measured by the determinant of x. So now if I have 1 over determinant of x, which is the same as determinant of capital omega, then that's basically will be the sampling density. So now what we are trying to do, our job is to find the smallest sampling density that will allow the signal to be reconstructed from its samples. That means to be able to reconstruct mean I don't have overlap when I do the replicas. Remember, I don't want to have overlap between this disk and this disk, right? At the same time, I want to have the smallest sampling density. So what does that mean? That means, yeah, here. Is this the smallest? No. If I can bring this disk to barely touch this disk, like this one, same thing in here. I can bring it here, bring this one here, bring this one there. They barely touch. There is some kind of gap between them. As far as I don't really make them overlap, then I can reconstruct. I can make every single sample represent more in this case. That means I have what? The smallest sampling density. We'll pick this up next lecture, and hopefully the remaining few slides in this lecture will make things a little bit easier. So at least for today, none of this material is included in the starred problems, However, there are many unstarred problems that really cover this because sampling will be part of the exam. So what I want to kind of do, what the takeaway today is extending the sample from 1D to two-dimensional case using rectangular. And from there, we managed to find the relationship between the Fourier transform, the analog, and Fourier transform, the discrete signal. And then we loosened up our constraint on the rectangular sampling lattice and make it a generalized sampling. And from there, once we have a generalized sampling, then we have these two vectors that really define our sampling, capital X in the spatial domain or capital omega in the frequency domain. So now the question is, how can we pick these? So the reason is there are two things to decide on how to pick these. The first one is to prevent an overlap. That means we will be able to reconstruct the signal. And the second one is to really, it has to do with the sampling density. We like to have the smallest, meaning what? Meaning the same sample, it can cover more, represent more in the analog signal. And we'll look at that in more detail next time. And there's some problems in the second problem set that govern this. Okay, thank you. Have a good Labor Day weekend. And don't forget, the homework is due tomorrow, Friday, for everybody, and Tuesday for section Q. And then by the time we come back on Tuesday, I will have all the instructions, all the timeline, and everything ready for the exam. And thank you for whoever pointed out that career day is happening next Thursday with different, with the virtual kind of meetings with the companies. I'll keep that in mind. So I'm hoping to have some 24-hour period that span into Friday, so you can really have the opportunity to pick the time that fits your schedule most. I will have more details ready for you by the time you come back from Labor Day on Tuesday. Have a safe weekend. Thank you.